So, good evening, everyone. Welcome to our guest lecture on artificial intelligence, particularly its applications in electric vehicles and smart grids, hosted by the Magister of Data Science at the Faculty of Science and Mathematics, Satya Krishnan University at Indonesia. So my name is Surya Satria, and now I am delighted to serve as your moderator this evening. So today we are truly honored to have with us Professor Yi Suan Hong. Oh, sorry
Yes,
for
yeah, exactly.
mispronouncing. That's good. Okay. Dean of the College of Technology and Engineering at National Taiwan Normal University. So Professor Hong will share his valuable insight on how artificial intelligence is transforming the future of electric vehicles and smart grids, enhancing efficiency, reliability, and sustainability in modern energy systems. So allow me briefly introduce our distinguished speaker. So Professor Hong is a respected academic and researcher in the field of technology and engineering with a strong background in AI applications, intelligent system, and smart energy solutions. So, as the Dean of the College of Technology and Engineering at NTNU, he has led numerous research initiatives, I think, that bridge academy, technology, and industry, fostering innovations across Taiwan and beyond. So we are very fortunate to have him with us today to share his knowledge and experience. So today's sessions will consist of approximately 60, maybe to 90 minutes of
Okay.
presentations. Yeah, it depends on your material. You can
Yeah.
prolong if you have much more material, of course, and then followed by 30 to 45 minutes of questions and answer sessions. So I thought Professor Hong maybe as kindly allowed the participants uh, may ask questions at any points during the talk. So please feel free to raise your hand or post your questions in the chat box. So we encourage everyone to actively engage. Your questions and comments, of course, are very welcome. So without further ado, let us warmly welcome Professor Ji Suan Hung from National Taiwan Normal University. Professor Hung, the floor is yours now, please.
Yeah. Thank you. Thank you for the introduction of Dr. Saya Satria. Thank you very much. And it's my honor to have a talk with you about the electric vehicles, especially the sustainability and the energy that applied to the vehicles. So it's my honor to briefly build up the fundamental knowledge about the transportations, because I know that you might be in the field of mathematical or computer science or informatics, but actually my expertise really focusing on the green vehicles and the application of energies, so that of course I will bring some like control strategies and how to communicate the controllers with our vehicles. But actually, I will briefly introduce the fundamental knowledge of the electric vehicles. Okay, but before that, please allow me to briefly introduce our school because we are very top one international schools, which means that the foreign students in our school that occupies the highest percentage, like 13% of the students are just from abroad. So which means we are really international university. So maybe I can share with you that our the status of our school. All right. So please. Okay. And can you show the slides?
Yes.
Okay, right now I just Please allow me to take some time to introduce our university. So here you can see we call the National Taiwan Normal University. So you may wondering what is abnormal? No, the word normal means the regulation because we have to cultivate the teachers for the junior high school, senior high schools, or the vocational schools in previously, so that we have some regulations. So that we call the National Taiwan Normal University. And actually, in average, our school is like a rank 6 or rank 7 QS in Taiwan. And we have 10 colleges at NTNU, such as, education is our biggest college. And also we have the liberal arts, science, technology, and engineering, which I belong in, and international studies and the social science, and industrial academia, innovation, management, music, and arts. Okay, so here are the key facts of our school. So we are benchmarked as one of the 4 university for bilingual education in Taiwan. And, we are the first in percentage of international students. So just like I said, right now we have 13% of the foreign students in our school. And we are the first in education, music, arts, and sports. But actually, our engineering and technology still goes up from the QS ranking. For example, the WE, the Department of Electrical Engineering, previously it is like 300 to 400 ranking globally. And we are the first in social science and humanity, and the second in academic discipline ranked in QS top 100 Taiwan. So here you can see that, please allow me to briefly introduce our college because I'm the dean of the college. So I think I have to introduce our college. So maybe you have the intention to study abroad to Taiwan, to NTNU. And also here you can see in 2024 QS ranking by subject, we are the globally QS 600 to 650 in computer science and information system, because we have another department of computer science in the College of Science. And also we have a 51 to 100 in engineering for petroleum. And of course, we have 3 Department of Engineering certificate by IEET and 2 IEEE fellows. And maybe right now is 10 faculties listed in the world's top 2% scientists right now. And so in our college, actually we can separate it into 3 groups. So in the middle column, you can see that we have 5 departments in engineering fields. For example, traditionally, we have a Department of Mechatronics Engineering, Department of EE, the Graduate Institute of Electro-Optical Engineering, and Electro-Optical Engineer and the Vehicle and Energy Engineering. So I belong to the Vehicle and Energy Engineering. And also we have a department in social science, such as the Department of Industrial Education, Department of Technology Application and Human Resource Development, and the Department of Graphic Arts Communication. And also we have one department in interdisciplinary field, what we call it the STEM education. So I think we have a PhD students from Indonesia. And so welcome all of you. Maybe you can attend this good program in the future. So here are the details about, from the left column, you can see Department of Mechatronic Engineering, including the Intelligent Automation Control System, or the optomechatronic integration system, or the precision measurement and sensing technology, etc. And in the middle part is Department of Electrical Engineering, including the system on the chip, multimedia and communication, and intelligent control, and the robotics. And right now in our college, actually the AI and the robotics and the semiconductors are three main streams of our college. So actually in this summer, we just developed a program called AI plus semiconductor program, so that will attract the attentions from the students from the Japan, the Kumamoto University, and the prefectural Kumamoto University. They are totally about 30 or to 35 students just come to Taiwan and learn the AI and the semiconductor technologies, as well as that we arrange, the Mandarin learning, like ni hao, xie xie, something like that. And because we have a very strong Mandarin training centers, as well as we have introducing the Taiwanese culture. So actually, I think that the program in the summer vacation can be opened from the students from Indonesia. So the students in Indonesia who are interested in AI technology or the semiconductor, that you can come to Taiwan, and we will provide it, all the courses, and yes. So maybe we can talk about later on. Okay, so you can see we have just like I talked about the program of electro-optical engineering. And here are the Department of Industrial Education that cultivate the talents for the junior or the senior high school teachers. And also we have the Department of Technology Application and Human Resources Development. And we have a Department of Graphic Arts Communication. Yes. And at the left-hand side, you can see the program of vehicle and energy engineering. So it is related to what I'm trying to say, the topic that I will discuss. We'll discuss the advanced vehicles, including the hybrid electric vehicles, the autonomous vehicles, electric vehicles, engine vehicles, or how to use the green energies and energy technologies, and the intelligent power systems. And the right-hand side is the STEM education program, and it is only for the foreigners for the PhD degree. So maybe you can discuss me later for that. And right now in our college, it's only 4 students from Indonesia. So hopefully the number of the students goes up after this speech. Yes, I hope so. And because we are very internationalized, so you can see there are many what we call it the English immediate instruction courses, which means that courses including the materials, the lecturer, the language, all talk in English. So it is more convenient for you to know what is the contents of the courses. So right now in our college CTE, we have totally 84 EMI courses. And if you want to study the graduate program in English, you can see with different department, we have a different program like this. So it's very convenient, and you can choose any of the interesting field that to go abroad, go to Taiwan, come to Taiwan to learn, to get a degree. And of course, here are the application schedules. And of course, we have some subsidies or fundings So here you can see we have scholarship opportunities. Uh, the left side column is from the Ministry of Education, and the middle part is the NTNU scholarship from our school, and the right hand side is from our college. So totally, I think to make it more easy to live in Taiwan. And of course, we have in our college we have international partners of our college uh, in the areas of North America, the Europe, or the Asia. So basically, maybe we can have further cooperation in the near future. Okay, so here are the briefly introduce uh, the uh, the NTNU. All right. So all right. So right now, please allow me to go to the our courses. Okay. Is there any problem? After briefly introduce our school.
Great. Maybe Hannah will help the students if they want to go to you because we have already what MOU
Oh, yeah.
signing together. So if they want to go to your place, we can have as the bridge between you and the students.
Yes. Yes. Okay. Right.
Okay,
So
please continue.
okay. Thank you. Okay. So please allow me to go to the our our speech. All right. So because I'm an engineering guy and especially for the mechanical engineering, so just like I said previously, I will briefly introduce what is the advanced vehicles as well as how to modeling it and as well as how to control it. So I think today my topic is the system dynamics modeling and the control algorithms for advanced vehicles. Of course, I will briefly introduce the control strategies that applied the AI strategies. All right, so this is the outline that you can see. I will give you a vision of what is the trend of green vehicles and following by the modeling of advanced vehicles and the software design of the controller and how to manage the energies and the control strategies. And the fifth part is because you have to develop your controller, so you have a real-time simulator, and I will I will explain what is the purpose of real-time simulation and what is the definition, and the sixth part is the application. All right. So why do we have to produce the green vehicles or advanced vehicles? Of course, you may know the climate change. So reported from the Intergovernmental Panel on Climate Change, it says that from 1970 to 2010, the increase rate of the pollutants is 250%, where 80% is from the on-road vehicles. So here you can see the blue area. This is from the road. So which means that we have to decrease the pollutions uh, from the road that you have to produce the green energy vehicles urgently. And sorry, but here you can see here is a number because here you can see some Chinese characters. So just ignore it. And you can see a number that 1.78%, which means that the energy produced in Taiwan only 1.78, which means 98% energy has to be shipped from the road to Taiwan, and that will increase it is a highly concern of these the safety because mainland China is beside us. So if it you know sealed our coast, and there is no shipping like the natural gas to Taiwan, will encounter a very serious problem that the energy, the electricity will deplete it, and that will cause a serious problem. So what we're trying to do is to build up many solar systems as well as the wind turbines to collect the energies from nature. And here is a figure that you can see the energy consumption for the American people daily life. And you can see the left-hand side, there are different types of the energy, including like the solar, the nuclear, the hydro, the wind, the geothermal, the natural gas, the coal, the biomass, and the petroleum. But you can see that all of these energies that can be transferred into two main types. The first one is, you can see in the middle part, the brown one, the electricity generation. It occupies 37% of the energy that totally used for the American people. And the right-hand side, downside, you can see the transportation. It takes 28% of the total energy, but it is very shocked that only 5.93% is useful energy, which means that more than 80% of the energy from the gasoline has been wasted, maybe from, just because of the waste heat generated by the engine. So which means that we don't want to use the engine anymore. We just want to get rid of it and get a more high efficiency power sources. So you can see that the motor is a good candidate. All right, and here you can see the stringent fuel economy regulation. So the x-axis shows the year, and the y-axis shows the kilometers per liter of gasoline equivalent, normalized to US CAFE test cycle, which means that in different areas, for example, in the pink one, it is from Europe, and the blue, the yellow one is Japan, and Korea is a red one, and all of this line shows the increased tendency. That is because we have to make the liter per kilometer, the index more high, which means that you will save more fuel. And this is the regulations of each countries or areas. And also here you can see that, again, the left-hand side shows different types of the energy that can be transferred into the three types of the energy carrier, including the liquid fuels, the electricities, and the hydrogen. So corresponding to different types of the vehicle. So you can see the pink one is a conventional internal combustion engine, why we call it the ICE. And the second one is the ICE hybrid, which means that you have to combine the engine and the motor to form the hybrid vehicles. And of course, if you increase the size of the batteries and also the motors, and then you have and also you have an onboard charger, then you have a plug-in hybrid IC vehicles. And if you get rid of the engine, what you only have is the motor and the battery, then it is electric vehicles. And the downside, the bottom side, you can see it is fuel cell electric vehicles, which is the energy supply is from the hydrogen, because hydrogen with the oxygen come from the air, combined with the so it is the chemical reaction. So there you again the electricities to provide the electricities to the batteries and to drive the electric vehicles. So here you can see that different types of the technology roadmap. So you may see you may know that there is a very big automotive manufacturers called Toyota, and they have 3 steps for the green vehicles. The first one is that we have to improve the conventional powertrains with different, the control of the engine, different continuously variable transmission. And then the middle stage is the hybrid vehicles, which means that your engine vehicle that should be equipped a motor that responsible for the powers with the engine simultaneously, which that will decrease the total energy that used in the vehicle. And the final stage is the fuel cell vehicles, just like I said, because hydrogen plus the oxygen, the chemical reaction, the only production is only water. So which means that you are not produce no any pollutants. So that is the ultimate goal of the Toyota. And so here you can see that with different types of the green vehicles, including the battery electric vehicles, range extension electric vehicles, what we call it EV in abbreviation, and the plug-in EV. So you can see different brands of the automotive manufacturers. They have their own green vehicles. Right, so you may encounter some problem that it is out of batteries or battery energy, so that we have some charging vehicles that carry the high electric capacity batteries to charge the vehicles if your electric vehicles is with low power. And also in Taiwan, we just produce several types of the electric vehicles. So right now, I just have cooperate to have some project with our government that they want to produce the logistics vehicles. And for the logistics vehicles, here you can see it at the left-hand side, bottom side, it is a truck. So the truck is electrified. So it is provided by the motor for the traction. The traction motor will drive the vehicle. So it is an electric truck, as well as you can see the container. The container here, because you have to let your goods under like minus 20 Celsius degrees. So that means that you will have a refrigeration for the cabinet, so that you will use the electric energy as well. So actually, I'm doing some research how to properly distribute the electric power for the traction and for the cooling system. That is a very a very good research topic. Right, and here is just briefly introduced. There are many brands just produce the fuel cell vehicles, no matter what kind of the international automotive brands. So you can see GM, you can see Volkswagen, you can see Hyundai, you can see Nissan, the Honda, Toyota, and Ford, etc. And of course, in Taiwan, we just produced the fuel cell electric bus, because actually we are very good at building the bus system in Taiwan, and we just export to different countries. So for our government, they just provided the funding for our bus operator to produce the fuel cell electric bus. All right, and for the green electric vehicles, here you can see the hydrogen-based ground transportations. So because just like I mentioned that you have to get the hydrogen to provide the chemical reaction to produce the electricity to the traction motor. So how can you get the hydrogen? So of course, ideally, you can use the solar energy, the wind turbine, the biomass, or the nuclear electricity to electrify the water to produce the hydrogen. And then you just compress it into the hydrogen tank and distribute it to the hydrogen supply station. And then your vehicles with the hydrogen, with the fuel cell inside, that you have to get the hydrogen supply so that you can make your vehicle run. So this is the whole process, how to create the hydrogen and how to deliver the hydrogen to the fuel cell vehicles. And the fuel cell electric vehicles, the efficiency goes up to 70 and 80%. And you might know that for a traditional engine, the total energy efficient is only 20%, which means that your vehicle using the fuel cells is 4 times higher of the efficiency compared to the traditional engine. But of course, it has some drawbacks that the system is very complicated and with a higher cost and the slow transient behavior, because you have to do the chemical reaction to produce the electricity. Okay, and another the most popular green vehicle is what we call the hybrid vehicles. So a hybrid vehicle has at least 2 sources of motive power. We have prime, like IC engine, fuel cells, gas turbine, and also we have power assist power sources such as the batteries. We have flywheels, ultra capacitors, and hydraulics. And its most popular hybrid vehicle that you can see on the road is what I don't know. Maybe in Taiwan, it's very popular of the hybrid vehicles. The most famous brand is Toyota Prius, and it is equipped with 1 engine and 2 motors. So here is the classification of the hybrid electric vehicles that we are just like the electric circuits. We decide what kind of hybrid depending on the energy flow. Like if the energy flow is in parallel, just like the top left-hand side. And here is the serial, and also it has a power split hybrid. Okay. And just like I mentioned, when you increase the battery and also you increase the motors, and if you have an onboard charger, then the hybrid vehicle becomes the plug-in hybrid. So which means from the left-hand side, you can see here is a figure, and the x-axis shows the travel distance per day, and the y-axis shows the ratio. So here you can see if we design the battery electric capacity that can let your vehicles travel like 50 to 60 kilometer per day, that you have the chance like within 70 to 90% of the chance, you don't really need to use the engine, because your battery has the sufficient electric power to drive the vehicle. So which means that during Monday to Friday, when you go to work and back home, what you only need to do is that the power is only the traction motor. But during the weekend, when you want to travel for a long distance, you can see the engine with the generator can be a power assist power that provided extra electricity to the battery. So which means that it will extend the traveling range of the vehicle. Okay, so here there are many types of the plug-in hybrid. Okay, so you have Toyota Prius, Nissan, GM, and Ford. And also maybe I think 10 to 15 years ago, in India, there is a new energy that produced for the vehicle, and it shocks the world because in India there is a very big automakers called Tata. So they just transfer the technology of the air engine from France. So so the engine just like a traditional gasoline engine, but the input from the input port is a compressed air from a big tank. So it will produce no pollutions. So you can use a compressed air in the city traveling. All right. So thank you for listening to the briefly introduce of the advanced vehicles right now. So if we want to develop green vehicles, or if we want to evaluate what is the performance of the green vehicles, then we have to modeling. And we have to use the numerical simulations of advanced vehicles, right? So when we are doing the research, we are not really put the vehicles on the road or on the track to test its real pollutions or the fuel consumptions or the electricity drops. And instead, because we have to greatly introduce the human resources or the develop time, the shorten the R&D cost, then we have to do the modeling because when you do the modeling and the numerical simulation, it will save a lot of money that you don't really need to do a lot of calibration. What you have to do is to build a model that's similar with similar dynamics with real vehicles, and then your computer just become a virtual vehicle. Right. So actually, in the commercialized software, we have a different software packages. I just briefly introduce it. So maybe I can provide the slides to you, and if you are really interested in the vehicle dynamics and how to simulate the performance of the vehicle, then you can see the slides. All right. So just like the car sim simulation commercialized software. And you can see if you enter the key parameters of a vehicles, and then you can construct the environment of the road, or you can construct the the climate. You can construct the road with a different roughness, and so the vehicle will have a different energy consumptions. And then you can analyze, the 3D dynamics of the vehicles. So before you produce real vehicles, okay, maybe I can choose a small engine. Maybe you can choose big number of gear reduction ratio. Maybe you can choose bigger batteries so that it will achieve the goal of the traveling mileage that I set the goal previously, right? And besides the four-wheel vehicles, we have a simulator called the Boxing that in the commercialized software, you can see that in the right-hand side figure, you can enter different types of the geometry parameters, and so actually for the commercialized software, it constructs the dynamics equations and then it will calculate what is the performance. And with a 3D representation, just like these figures, so that it will make you more visualize how the scooters or the motorcycles run. And of course, it will have the chains to slide out of the road, so that you can, so you know how to prevent that dangerous situations. Okay, and of course, the extension of that software is the truck sim. So, for example, in Taiwan, our government encouraged us to produce the electric bus and also the electric truck. But before we have to real produce it in the manufacturer, the factory, then we have to do the analysis. So that we will use the simulator, just like this kind of simulator, what we call it the truck sim, that you can develop different road, you can develop different flexible truck uh, that you can see what is the performance. And it can show the animator. Okay, and because in Taiwan, actually we are really focusing on the autonomous vehicles, and we use different types of the commercialized softwares to simulate the autonomous vehicles. Of course, we can set different environments such as the rainy day, the cloudy day, or in the tunnel, and also we can construct the parameters or the performance of the vehicles, and we can choose different types of the camera, the LiDAR, the radar, so that we can see what happened if the resolution of the CCD camera failed or something like that, so that you can do the simulation to see the sensors that you equipped in an autonomous vehicle is suitable or not. Okay, so that you will have some animation that you can see our autonomous vehicles, the fleet, or how if you want to bypass the vehicles in front of you, and you have to bypass to another lane, what will happen? Then you can do it not only on the road. Before that, you have to do some preliminary studies, so you can construct the models on your computers to save the money. All right. And then for the key components, actually in Taiwan, we have many uh, like high power electricity equipment provider. They create many like the battery charge and discharge test system. So what they're doing is that they just modify the power supply to, but with some equivalent electric circuits to emulate the dynamics of a battery, so that you can modify a power supply just like the behavior of the battery. So the simulator, the battery simulator, and then can be connected to the like the PV or what we call the solar systems, and to the grid to see what happened. And this is a very cost effective, because um, with different situations, you might have to build different types of the battery with different number of the serial and the parallel. But right now, what you only need to do is to set from the GUI, and then to set what is the power supply can be transferred to an equivalent batteries. So it saves a lot of money to do many experiments. All right. Okay. So the software I just described to you is more like a system level. It is more macro scale, macro scale simulation. But if we want to go inside into the details of the like the battery or the motor, and then we have to construct, we have to discretize the systems into a grid, and using the finite element and any other governing equations to to simulate the distribution of the temperature or the stress or the power or any other parameters on the surface or inner system. So for example, here is a very famous the commercialized software, what we call it the ANSYS. And under the ANSYS, there are many sub-program, such as the Fluent is for the fluid and the heat analysis. And here there is a sub-program called Maxwell. Then it is used to analyze the electricity and the magnetic field, such as etc. So here are some examples that you can see that using ANSYS, and then you have the thermal management. You can see the battery structural reliability, because for the testing of a battery, then you have to like have a thrust to see if it will have a short circuits to cause the dangers of the battery. And the right hand side, it is used for the battery management system. And so, okay. Okay, so here are any other different types of the simulators for the battery and the green energy, such as the Maple Sim. You can simulate the dynamics of the battery, as well as you can see the third graph is paragraph. It says the state of health. So the state of health means the life of the battery. So if the state of health, if the battery is just come from the manufacturer, the state of health is 100%. But if the electricity of the battery runs out, for example, if the life cycle reaches 1500, which means the total electric capacity just remain 80% compared to the original battery. And then we can define the state of health reaches 0, which means that you have to replace that battery. So that you can see here is the simulators to evaluate what is the state of health of the battery. I think it's very important if you are doing research about the electric vehicles. And also I think you might know there is a very popular and very famous commercialized software, what is called the MATLAB. And in our lab, we use a lot of modules of the MATLAB. For example, we use a graphical block set to build up our program, what we call it the Simulink. A Simulink is a very powerful toolbox that you can only drag and drop, and then you link all of this block set together, and then you can see what's going on graphically. So it's very user friendly to analyze the electric vehicles, the green vehicles, etc. So in our lab, truly that I recommend you to use the MATLAB, because MATLAB can, if you are doing some research in different fields, actually MATLAB is industrial. It's very famous for industrial applications, even in the biomedical even in the financial, many applications or toolbox or the freeware is from a MATLAB. So maybe can be for your reference. Okay, so here are some examples that we will use module that has already constructed from the company, and then what we need to do is only to entering the parameters so that we can form vehicles. Okay, so here are the transmissions, and here just what I said, that because in a electric vehicles, the key components is the motor. So when you design the motors for electric vehicles, you can be separated into different fields for evaluation. So firstly, such as the electric and magnetic field analysis. And the second one is the thermal transfer and the fluid analysis. Or the third one is the structure analysis. And the fourth one is the vibration and the noise analysis. So under the ANSYS, there are many subprograms that can analyze all these factors for a motor. So it's very powerful software packages. All right. And because the above that I introduced is a commercialized software, but sometimes because the flexible of the software is not very high, and you want to modify it, or you want to establish your own system, then you can create your model by yourself to draw and drop the block set to form the motor. So for example, this figure shows that we use the MATLAB and Simulink to build the motor dynamics. But you have to know that when you build a motor model, if you want to make it more real, like a real model, then the data has to be measured from the real world. So for example, at the bottom left-hand side, you can see here is the testing bench for motor, so that we will retrieve the data from the measurement data, for example, different rotational speed or the traction torque, and what is the efficiency. Then we can construct a map like this and provide it to the model, so that the model can be a virtual motor. And so here you can see here is the construction of the motor testing bench. So after we establish this bench, we can retrieve the data, and then we can get the data to form the model. All right. Similarly, for the battery of the electric vehicles, and so here you can see at the top left-hand side, it's a unit cell, and then you combine the unit cells to form a module. For example, you have the 6 in series, 6 unit cells in series, and at the top of the module, here is a board to modulate, to supervise the temperature and the voltage and the current of the batteries. And then if you combine these modules together to form the package, just like the top right-hand side, and then of course you can test the package using the charge and the discharge battery testing systems. And after your experiment, and to verify the performance or the characteristics of the package is okay, and then you can equip the battery package into a vehicles. So here's the whole process, how to equip a package from unit, from module to the package. And then of course we have to design the battery management system and also the module management unit that to supervise the voltage or temperature or the current of each cell. Okay, here just provide the information of the electricity of the battery that will be influenced by the discharge current and by the temperature. Okay, so when we want to build up the battery model to see what is the key performance or the transient dynamics of the battery, what we need to do is to identify what is the equivalent circuits. So actually, you can use different measurement approaches to get the values of the resistance, the value of the capacitance, the value of the reluctance, or the key components of the equivalent electric circuits. So that means the equivalent circuits stands for the batteries that you used. So again, when we build a model, what we are really afraid of is that garbage in, garbage out. So you have to ensure that the model that you built, that the performance, that especially for the dynamic performance, should be very precisely overlap with the measured data of a real battery. So that is surely that we have to focus on. Okay. So here you can see we have two types of the typical model for battery. The left-hand side is a resistant model. So what you need to do is to define what is the equivalent resistance in the battery. And at the right-hand side is more precise to describe the dynamic model of the battery. But the drawbacks is that you have to measure, or you have to define, or you have to identify like RE, VCB, RC, VCC, or RT. So that you have to identify 5 key parameters. That it is very complicated compared with the resistance model, right? And of course, for the drivetrain, and we can see from the rule book, and it will show the gear ratio. Then we just construct it in the model. And here is one first order dynamics of the vehicle dynamics model that using a very simple ways, F equals to M plus A, M multiplied by A, so that the traction term subtracted from the air forces, subtracted by the rolling resistance, subtracted by the grade resistance, and subtracted by the braking force. So that you will get the transient velocity of the vehicles. And then you just combine all my mentioned block set, and then you just link them together, and then you can get the performance evaluation. Sorry, this is written in Chinese, but which means that here there is a very famous motorcycle manufacturer called Kimco. I think this is a number one scooter or motorcycle manufacturers in Taiwan, and they just give me a project to evaluate their electric scooters. So what we have to do is to let them provide us the key parameters, so that we can evaluate what is the electricity consumption and what is the variation of the velocity. And of course, you have to provide the contour of the efficiency with respect to different rotational speed, as well as the torque. And then after you construct the contours, that you have to insert it to the, just like I mentioned, the simulate model of the scooters. So here are the very briefly introduced. Here are the results, and you can see we can evaluate different motor power, the efficiency, and we can see we can evaluate the voltage of the battery, the current of the battery, or the SOC. The SOC is not a system on chip because we are not in the double E. In mechanical, SOC means state of charge, means what percentage of the electricity remained in your battery. So what we call it is SOC. Okay. All right. So here are some examples that our lab just built in different industrial academia projects uh, of our lab. Okay, so firstly, you can see that we just built a 3-mode range extender electric vehicles model for commercialized vehicles that produced in Taiwan. Again, the manufacturers have to provide the performance map of different power sources. So what you can see in the right-hand side, we have a contour to show what is the efficiency distributed under different rotational speed and the torque conditions, right? And okay, so this slide is very interesting, and because we have a racing car competition in our universities, and anniversary we have a competition so that each university will build up their own racing car uh, at the so in our college we just win the first prize, and because we have done a lot of simulations to choose the proper batteries and the proper motors and the proper gearbox. All right. So what we're trying to do is that at the top left-hand side, you can see here is the lane or the track for the competition. So we just build up the track um, like the numerical profiles in the middle part. And then we just construct the racing cart models, just like I mentioned, like the electric scooters. And then we can simulate all kinds of simulation. And then we just put the operation points into the efficiency contour of the motor to show, okay, and if the motor is operated in a very efficient area, if not, we will modify our gear sets to let our motor runs at the very efficient areas. So that I think before the experiments, what you have to do, not only for the automotive research, but I think in mechanical, in electric engineering, or in chemical engineering. So you will have different types of the simulation tool to simulate uh, before your experiment. Okay, here is another project that provided by the research institute. So we construct a hybrid hydrogen fuel cell bus because our government just want to promote the hydrogen fuel cell bus in Taiwan. So I'm just to help to build the dynamic model so that our government will have some reference to see if it is worth to have to support the strategies for providing the hydrogen fuel cell bus. Okay, here are the modeling results. And also we have built another, the models, such as, in a green vehicles, the power sources or energy sources are significantly influenced by the temperature. So, for example, the optimal fuel cell temperature should be operated like 55 degree to 60 degrees Celsius. And if you want to operate lithium batteries, I think the optimal temperature should be 35 to 40 degrees Celsius. So that in our lab also we have produced different types of the thermal dissipation systems, thermal management system, or what we call the cooling system. And before we construct a platform, what we need to do, of course, the same. We have to build up the thermodynamic equation, just like you see in the middle part of the. Of course, we have some papers about that. So here you can see that after we build up the thermodynamic equations to the Simulink, at the bottom left-hand side, you can see here are the software, and then we can build up a real platform for a thermal management system. And so at the right-hand side, you can see we use different control strategies for temperature management to allow the fuel cells and the batteries that operate at their optimal operation temperature areas. All right, and not only for the vehicles on the road, but also there is, a vessel manufacturer that they provide us a project that to create a model for their vessel. So the vessel can be a ship, can be a ferry, or can be the submarine. So with different types of the vessels, you will have a different type of the dynamics equations to build up. Okay, so here we can see different. So that at the right hand side we have a lot of simulation results. Okay, and okay, so this vehicle dynamic model, just like I said, just the electric refrigerator truck. Also, so what I want to stress is that if you want to build a system level model, your model should be very easy to abstract the key characteristics of the subsystems, because your model might be run maybe for I don't know, maybe 10,000 seconds or 110,000 seconds, something like that. So you have to simulate for a long time. But considering the CPU and your RAM, your memory, then your model should be as simple as possible. But also you have to accommodate the accuracy of the subsystems, all right? Because you have to verify your control strategies later on. Okay, all right. So here are the okay. So after you model a system, then you have to control it. So for the control units, it can be separated into two groups. The first one is what we call the supervisory powertrain control system, and it concerned about the fuel economy, emission, drivability, and it's a long horizon and the slow dynamics. Because in a vehicle, the vehicle mass is very huge. So no matter how fast you press your pedal or press your brake, the speed of the vehicle very, very slow. So actually for the vehicle control unit in the higher supervisory powertrain control level, actually you don't really need to very fast response. So for example, the sampling time is like 0.05 seconds is sufficient for the control. But contrary, if you want to give the commands to the the component level uh, systems, then for example, if your vehicle have engine, then you of course you have an engine control unit. If your system has a motor, you will have a motor control unit. A battery have a battery management system, etc. And this kind of subsystem control unit is characterized by the transient response, a very fast transient response, because that you have to control, for example, the ignition period, or the current, or the switch of the like the diodes, like the MOSFET or the IGBT, in a very few seconds. So which means that it's your controller should be very with fast response compared to the vehicle level control units. All right. So here are the software that this is the environment that we build up our models. So for example, you can see it's it's not a commercial, but we just build it on that user friendly platform. We use it to build up the model on MATLAB and the Simulink, etc. All right. So here is an example of the vehicle control unit. So the left-hand side column, the yellow one is the inputs signal, including the pedal, the brake, and the gear command from our driver, as well as the subsystems from the batteries, from the gears, and from the motors. And after the simulation and the evaluation, what the subsystem command is, and then we just deliver to the blue one. So for the blue one, the output should be the torque or the speed commands for the motor, the generator, or the different modes, switch, something like that. So it's the configuration of a vehicle control unit. So you can see the left-hand side, and in the middle part, in the central, it's a vehicle control unit. So we call it VCU in abbreviation. So it will link to different subsystem CU like VCU, ECU through the CAN bus. And then uh, the developed software of the VCU should be downloaded to the controller. All right. Okay, so for the energy management system, if your vehicle, just like I mentioned, if your system has two power sources or two energy sources, that you have to appropriately separate the power under different situations, such as the battery state of charge, the demanded power, or the velocity of the vehicle, etc. So that we have to use different algorithms to calculate what is the proper power that should be commanded to the power or the energy sources. So at the left-hand side is the role-based control. I think you might very familiar is that when we programming, we will use if, else if. So it is very popular for the vehicle control rules, if else rules, or we will use the fuzzy logic with an expert system to define, different and the membership function to define what is big, what is middle, what is low, to properly distribute the power. And at the right hand side is the theoretical based control. And because we have to optimize, like the total energy. Then we have to minimize the total energy that we used under a specific scenario of the driving road. And then we can use what we call the dynamic programming, or the equivalent consumption minimization strategy, to let our index optimized. Okay, so here is a rule-based control. It's a tree diagram. You can see that it is a very fundamental based on the engineering intuition. And so first, on the top, with the vehicle speed, we can define if it is greater than 0 or not. And we can define if the power is bigger than demanded power or not. And then we'll have the third level is like if we should charge the ultra capacitor or not. And then the button is like we will charge the battery. So that you can use a tree diagram to very quickly to build up your rule base and to download it to your vehicle control unit. But because it is only for the engineering intuition, so which means that efficiency should be low compared to the theoretical analysis. But it is very easy to be implemented to the vehicle control unit. Okay. And here is the similar one. Okay, here is the theoretical concept. If you have two energy sources or two power sources, so what you need to do, for example, you have to minimize the equivalent field of the vehicle. So here is an example that for the engine motor hybrid vehicles. So how can you define or how can you do the fuel and energy management? What you need to do is to transfer the electricity of a battery to the what we call it the equivalent field plus the original fuel consumption from the real engine, and combine them to get the total equivalent fuel. So with a different power distribution, you will have different equivalent fuel, so that you can decide what is the power split ratio between the engine and the motor. Okay, but I think we are run out of time, so I'll just go quickly. Okay, so for the AI, I think there are many strategies for AI that are used in the vehicles if the vehicle dynamic system is very complicated, or the optimized parameters might be like 6 or above 6, and then we will use some evolutionary algorithm, or we can call it the biometric algorithm. So the evolutionary algorithm is defined by it is inspired by observing animal behavior or natural phenomenon to efficiently search for the optimal solution. And I'm not quite sure if it is commonly used in the computer science or informatics, but for mechanical system, usually if we want to search for the optimal solutions, sometimes we'll use the evolution algorithm, because online there are many freewares to construct different types of the evolutional algorithm. So what you need to do is to change it to your own field. So actually, for my master students, they did a lot of research. They downloaded many evolutionary algorithms, and so they can easily get the results and write their dissertations. So they will have a free time to dating with their girlfriends or boyfriends, whatever. Okay. And the second one is that it's typically applied in vehicles for optimal parameter search, system identification, and hybrid energy management. And just like I mentioned, because it is a low technical barrier, so for the master students, it can be quickly get started because you can download it, the freeware, the template of the program. Of course, you have to use it in your field. And so the open source program available is will enable the professors to launch a second peak of research. So actually, if you have a controlled plant and what you have to, if you want to create a new topic, and then you can search for a new evolutionary algorithm for your existing system. So please allow me to briefly introduce some of the the evolutionary algorithm. The first one is a particle swarm optimization, what we call it the PSO, and it is the most common, the evolutionary algorithm, and we just use it in the hybrid electric vehicles. And I think the main how to say that, the thing is that it's just to emulate the society of the birds. So here you can see the fat birds, what we call the king of the birds. It can search for the most foods compared to other birds, so that um, each birds distributed on the on the surface, which means it is one of the solution. For example, you have 10 birds. 10 birds distributed on a surface. You can search for different search for different food, search for food in different area, and we can compare the 10 birds to see which birds search for the most foods, and it will be the king of the birds. And other birds will be influenced by the king of the birds, but also it will be influenced by its own experience, so that we will use the vectors like this. So the first equation is the the vector of the velocity, and the velocity will influence the position of the birds. So which means that when you have 10 birds on a surface to search for the optimal solutions, and then it will influenced by its previous experience, as well as will be influenced by the king of the birds, so that you can quickly to search for the global optimal solutions. So what we're trying to do is use this kind of concept for the hybrid electric vehicles. And the optimal control variable is the power distribution ratio between the engine and between the motor, which will minimize the total energy consumption of a hybrid vehicles. And we just published this paper in a famous SCI journal called Energy, Apply Energy. So we have 10 birds, and to search for the optimal power split ratio to minimize the total fuel consumption of the hybrid vehicles. Okay, so here are the simulation results. So we just skip it. All right, and the second one I would like to share with you, it's very interesting, is what we call the bacterial foraging algorithm. So it is, emulate the bacteria in your organ, and it should search for the nutrition. So it will has different types of the movement. The first one that it goes straight is what we call the run, and the second one is that it will change the direction, is what we call the tumble. and you use the run and the tumble at different time steps. And so if we have like 10 bacteria over the whole vector space, and then you can find what position is with the most rich food or nutrition, then that is the optimal solution. So it emulates the behavior that the bacterial searching for food. And in our lab, we also do the research for finding the optimal parameters using the whale optimization algorithm. And because when the whale search for the food, and it will create a circle of bubble to trap the shrimp in the middle of the circles. So basically, this algorithm just to search for the optimal solutions based on two steps. The first step is exploration phase that it will search for the region with rich food, and when it search for the good area with rich food, and you will do the shrinking encircling mechanism. So yes, there's two steps that you can search for the optimal solution. Okay, and then we just use the whale optimization algorithm in our vehicles. So similarly, we will, because in our vehicles at the left hand side, we'll have the engine, the generator, and the motor. So we have three power sources, and then we have to decide it their power at each time step. Okay, and at the right hand side, you can see that we use two um, industrial computers to link to each other. So the model will run in real time. I think the real-time simulation is very important to us, because if we want to evaluate the controller is with a good performance that can be delivered, receive the data from the subsistence, calculated the algorithm, and deliver to the subsistence controller within a one step, then we have to build up the real-time environment to test the controller and the control strategies. So at the right hand side, you can see one computer is for the control strategy at the left hand side. And at the right hand side is for the vehicle dynamics that I just mentioned. And then you can communicate it with the analog and to digital, or digital to analog, or the campus. And then you can run in real time to verify your control strategies, etc. Okay, all right. And the third one I would like to introduce you is the gray wolf optimizer. What we call it the GWO in abbreviation, and it is very interesting that all these particles or all these solutions, or what we call all of these gray wolves, can be separated into four groups. The first group in the top of the pyramid is what we call the leading group alpha. And the second one is the strategy provider beta. And the third one is the prey management. Well, this is gamma. And all of these other gray wolves is what we call omega. So with different groups, we will follow the leader group alpha, and it will change all of these wolf steps in omega to reach toward the group of alpha. So it just emulate the behavior that the gray wolves searching for their food. Okay, so because this is in Chinese, so just skip it. So with the GWO process, we will search for minimize electricity consumption. Because in our vehicle, we have fuel cells, we have batteries, we have supercapacitors. So that we have to minimize the total electric energy that we used. And then we will do the comparison with different evolutionary algorithms, something like that. Okay, so again, we use two industrial PC computers. One is for the vehicle control unit, and the other is for the vehicle systems. So you just combine these two computers together to form a virtual vehicle linked to a virtual vehicle control unit, so that you can verify if your control strategy is suitable for the vehicles. And just like I said, when you do the real-time research and real-time simulation, it will fast and early system design changes. And because you are under the simulation, so the test cost can be reduced, because the what we call it the hardware in a loop is a repeatable environment, and you can reduce the developed cycle to develop your controllers. All right, so here are some examples of the international brands for the real-time simulation. For example, and at the right-hand side, here are three machines. Okay, so before that, you produce hybrid electric vehicles. At the left side, the big machines stands for the transmission. So once you download the transmission dynamics equations or the models into the machines, and it will operate it in real time. And in the middle parts, it is a machine to run in the, in real time. It is for the engine, and the right hand side is for the electric machines, which means the motors. So when you combine the three big machines together, and then you can get virtual hybrid electric vehicles in real time. So then what you can do is that you can link the control unit to each or to all of these machines, so that you don't really need to test on the road. What you need to test, or you can calibrate your parameters of your control strategies with these machines, or what we call it, the virtual vehicles. So it will save a lot of time, because you don't really need to drive a car outside and for the testing. And if you run it on the road with different humidity or different temperature and different road conditions, you will have different results. And that's the thing that we don't want to see. So using the real-time simulation with the industrial computers, you can save a lot of time and to really get the optimized results. Okay. Okay. So here is an example. I just skip it. Okay. So for the applications, yeah, we just did a lot of research about combine different energy sources. For example, in Taiwan, the electric scooter is very popular, but if we want to choose the location to set your charging stations or charging areas, and then you have to do some previous research. So what we help a fuel cell manufacturer is that we combine the fuel cells with the lithium battery to form a standalone charging station without grid, so that we can previously know that is there a suitable charging area for the electric scooters. And also, because in another industrial academia project, you know, the company want us to build up green area that with the solar energy, with the solar panel, with the fuel cells and the lithium batteries. And before that, we have to decide which is the specification of each subsistence, so that we have to build up the model, just like I said, on MATLAB and the Simulink platform. So it is, you know, very easily to get the results to see um, the specification is under design or over design, to choose the proper specification of each subsistence. Yeah, and here is another industrial academia project examples that we have to construct the models to emulate a van that equipped with lithium batteries, as well as the the fuel cells. And then after we derive the proper control strategies, just okay, here you can see in the middle part, here is a multi-dimensional table. And that is derived from our evolutionary algorithm. This is a best solution. And then we will download it to a DSP to control the DC-DC converters to um, manage the power of the fuel cells and the lithium battery of a real vehicle. So at the right-hand side, you can see that with preliminary studies on the computers, because we build like the fuel cell scooters as well as their control strategies, and then we just download the optimal control strategies into the DSP to control the DC-DC converter of the scooters, so that we have a very excellent testing data to show that we have a very high cruising mileage using our control strategy compared with their multi-year calibration of the parameters. So which I want to say is that using the simulation to construct the vehicle dynamics, and after that you just control the control strategies for the vehicle dynamics models, and after the verified control strategy, you can download it to the DSP and then to control the real vehicle. This is the correct process, to develop your control unit as well as for the system or subsystem design. And of course, we also do some research using the industrial computers for the virtual vehicles at the right-hand side. And we use the red one that you see, what we call the New Eagle Raptors. That we can download the advanced driving assist system for the autonomous vehicles. And then we can combine the controller with the NIPXI RT system to form, a virtual vehicle testing platform. So that use the system that I introduced, what we call it, the car sim, and you input the algorithm for the autonomous vehicle, you can quickly bypass the obstacles, okay, the steering and the overtaking. And then after that, you can also see the key parameters performance of the vehicle. Okay, and I think that is, this is what I'm talking about today. And thank you for your attention. Thank you.
Thank you very much, Prof. So your lecture is very comprehensive, and for me, it's very tough also.
Yeah.
So I don't know the audience will absorb how many percent of your lectures. We are waiting for the questions, of course. Who has questions? Please raise your hand or write your questions in the chat box. So Professor Hung has already given so many things, not only AI, but also physics, engineering, and so on. And uh, I hear about fluid dynamics there, also thermodynamics, electromagnetic, and so on. So who has questions about green energy, maybe? Green energy or power trains, or maybe the most important is the battery.
Yeah, because I'm
Question.
not a computer guy, so I'm a mechanical guy. So I think today the main purpose is that I would like to share the basic concept of the green vehicles, of as well as that to introduce our university. I think it is very important.
Yes, yes. And we are usually making AI from data-driven AI. So in your case, you have a very complete approach from the technical thing, the machinery, vehicle, and so on, and then comes AI from the theoretical base, from the many of physics laws, chemistry, and so on. But also you mentioned some of them about AI, data-driven AI also, because we don't do a lot about the machinery, about the vehicles. But if we have data, then we think about what is the data speak out. So it is a data-driven AI. You have AI from rule-based AI, and then yeah, some laws AI and so on. Maybe we can combine it if the students love to learn about dynamics using ANSYS, or then using simulating in MATLAB, and then we make a um, what simulations, and uh, get the data from that simulations, and use uh, AI, data-driven AI to analyze that one, maybe.
Yes,
To,
I
yeah,
think,
something
for
like that.
example, uh, right now I'm doing some because in the green area we have because what we are trying to do is because we want to analyze if we want to build a green area, including the solar energy with the fuel cells, with the batteries, and with the grid, with the load. And because the price of the electricity varies with different time period. So we, as you mentioned, the data driven. So what we're trying to do is that with different time, the electricity usage, we can input to neural networks so that we can predict at what time, what is the circumstance of the energy that will be used, so that I can preserve the energy. For example, if the energy that will be used at 7 p.m. is more larger, so that we have to reserve the energy from the battery previously, and we will train that big data using neural networks so that we can predict the control algorithm of the system. Yes, I think that is one of the example. And another thing is for AI is using the data driven is that if we like to evaluate the 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 electricity remain in the battery, it is what we call the state of charge, and then or the battery life, and then we have to use the data that measured from the battery itself. So you use the battery under different temperature, under different current drawn, at different situation that we use charge or the discharge machine to draw the current or to recharge the current to the batteries, and then you can get a lot of data, and then we just feed the data to the neural network so that we can evaluate the state of charge or the state of the health of the batteries. So I think that is the two applications that I proposed for the data-driven. Yes.
Yeah, thank you. Question is, students, maybe you should go to Taiwan and if you want to make your own car, the small one. You ask now how to make it. Hey, no questions?
Halo, Prof. Surya.
Okay, Ardian, please.
Yeah, yeah. Thank you. Thank you. It's interesting for me. From the data science perspective, Professor Hang, what strategy are the most effective for dealing with missing on inconsistent sensor data in AI-based energy management system? How about your opinion about that?
Excuse me. Energy management system. You mean? Sorry again. I'm sorry.
Yeah, yeah. It's interesting for me based on your talks about the data data science perspective. My question is, what strategies are most effective for dealing with missing or inconsistent sensor data in AI-based energy management system?
What kind of? So because the communication is a lot of.
I can help you.
That can you type?
Yeah.
I don't know if you can type.
It is about the missing of data. You have many sensors in your system, and then
Yeah,
you want to use a neural network for maybe anomaly things, or but then you face with the problem. The problem is missing of data communications. So not all of data come to your computer. So what happened in this case?
I'm
So this
truly
is
sorry because
yeah.
I just can.
Okay.
Or maybe you
So
can
this is
type, or you can
yeah.
send me the mail.
Please
I'm
type,
sorry,
Leon, please type
Miss
the question.
Adrian, Trinity. I'm sorry because here's some disturbance. Can you just send me the mail so maybe I can,
Yeah, it is about
reply you?
data-driven AI, but the data is not complete because the lack or something wrong in the sensors. So lacking of data, how to deal with the AI in this case. Yeah, missing or inconsistent sensors.
Oh, that's it. Oh, okay, I see. I think it's a very interesting questions. Missing or inconsistent sensor data in AI. I think that in the energy management system, I think just like I mentioned that in PSO, the particle swarm optimization, I think it is most effective for dealing with missing or inconsistent sensor data because because for the energy management system, if you want to use the evolutionary algorithm, then you have to define a cost function. And in the cost function, there are many parameters so that if you're missing one or two sensor data, for example, the engine torque or the motor torque, and still you can use the previous data for the energy management system because it's a very complicated. But for me, I just can say that the particle swarm optimization should be the best solution if your system is missing the the inconsistent sensor or missing some data. Yes. Thank you.
Thank you, Prof.
Maybe
Now,
we
for
can
the
have a
students,
further discussion about that. Yeah, thank you.
Okay,
Yeah.
thank you, Professor.
Thank you, sir.
yeah,
Thank you, Miss.
if you want to know about PSO or something like that, you should come to the lecture of operation research in the undergraduate mathematics in
Yeah,
our
I
department.
think each evolution algorithm will have its own advantage and drawbacks. So, for example, yes, in PSO, it is very quick and very effective, and it is can allow you to use it with some missing data, but it will be trapped in a local optimization. It might be trapped in the local
Yeah.
optimization. So what you can do is actually I use another approach called the bee colony algorithm. So it's just emulate the behavior of the bee, bumblebee, the bumblebee.
B or
Or yeah,
N in colony also.
or as I
And
mentioned that
B,
bacteria foraging
yeah,
algorithm for the bacteria.
bacteria.
Actually,
Yeah,
I haven't finished the algorithm. Okay, so if you want to reach the global optimization, that is the way. So it because for example, you have 10 bacteria to search for the nutrition, and after you search for maybe 50 steps, and after that it will eliminate, it will cancel um, the the 50% of the bacteria that search for the lowest nutrition, and rebirth. It will get the rebirth or the copy from the same location of the best 50% of the bacteria that search for the best food or nutrition, or what we call it the optimal solution. So then we'll skip for the what we call the local optimization. It will reach for the global optimization. But the drawbacks is that the computational loading might be um, more
long.
more heavy compared to the PSO. So
Yeah.
I think it's a trade-off between different types of the evolutionary algorithm. Yes.
Prof, can you compare between the evaluationary algorithm versus deep learning? Because we study a lot about deep learning, but don't study about PSO so much here. Can you compare between deep learning and PSO or something like that? Why you so happy with PSO and friends,
Oh, okay.
but not
So
deep
I
learning?
think that the deep learning, if you mentioned about the like the neural network and the evolutionary algorithm, I think it's different because you know you just let, for example, if you want to build a model of you using the deep learning, the neural network, so you just regard the battery or the subsystem as a black box. You don't need to know what inside, what is the, just like I say, what is the equivalence circuits. You just feed the data. You just feed the data to input and output to train the weighting to form what we call the battery model. But actually, it is not a physical based model. So actually, you don't know what happened if you just replace the battery with another type of the batteries, then it is not constructed on the equivalent circuit. So you just regard it as a black box. You have no idea if we change to another spec, then what you should do. You should do with the deep learning structure or the neural network. But for the evolutionary algorithm, you still need to build the very simple dynamic equation of a system. For example, for the battery, you still need to build the equivalent circuits of the battery. And of course, you can use the deep learning to train the equivalent resistance. Yes, you can do that. But somehow I can know the key characteristics of the batteries. But if you build the battery dynamics only using the neural networks, you just send the data in, send the data out to feed the neural network to train the weighting, and you have no idea if we choose another type of the battery or the different power of the battery, and what will happen. You don't know. Yes.
Okay, thank you. Actually, in deep learning, there is also a method for solving the dynamic equations called by physical informed neural network, but it is complicated too. And PSO is much better, I think, in this case.
Yeah. Okay.
Any questions? Ada pertanyaan lagi? Questions? More questions, please. Pak Bambang? Is there no question anymore?
Maybe you can write me through the email or something.
Raf, I have
Yeah.
a question.
Oh, Pak Bambang, please.
Why do you use MATLAB, not Python?
And I think maybe 10 to 15 years when I contact with the MATLAB, I just love it because MATLAB, I think the MATLAB, the first version of MATLAB should be tracked back maybe 20 to 30 years ago. So with a long history of the MATLAB, many engineering, just like I mentioned in the beginning, the MATLAB is a very, very powerful engineering analysis tool because many freeware, many toolbox have been built up with in different application fields. So with the whole history of the MATLAB, actually the simulation environment has been built with a very strong and very friendly, very effectively, efficiently environment for the researchers. And for Python, of course, but it is just the beginning. But for the performance evaluation, or for if you want to really quickly to get fast insight into something, for example, the evolutionary algorithm. When you search on the website, you will see many templates, many freeware that was written by different engineers. So like my master's students, what they do is just download the templates and to transfer the parameters to become the vehicle. So it's just like 2 weeks, 3 weeks done.
Okay.
And it's very effectively. So so that's my opinion, is that because the MATLAB, the history of the MATLAB is with a very long history. It creates many modules or the toolbox, so it's very easy to use. Yes.
Okay. Thank you.
So far is that. Yeah.
Yes.
Thank you very much, Mr. Bang.
Yes, thank you.
Yeah. Bang in Chinese is great. Yeah, that's great.
Pak Bambang, you can try
Bang
to
is
use.
great. Very great.
Yeah, Bambang is great.
Yeah.
You can try to use SimuPy maybe. SimuPy in Python. SimuPy in MATLAB. SimuPy is in Python. That's right. But Simulink in MATLAB is much better in.
Okay.
Yeah.
Thank you, Rob.
Okay. Other questions? If you have still questions, please, other students. Uh, hotter and hotter.
I have question, Prof.
Okay, Leon, please.
Yeah, yeah. Uh, Prof, I'm interesting when you read your presentation. For me, uh, does we use AI in reality? Uh, how we use energy magnetics when we use AI, using AI from for reality? Uh,
Sorry, can
does
you
using does
type
using
the
energy magnetic?
message?
Uh, can you give example how to deal with magnetic energy
Yeah,
in
in
your
reality,
AI?
using energy magnetic when we in reality, in the context of reality.
I I think how to
Using
optimize
sorry,
magnetic energy.
I'm cannot really clearly what you say. Sorry, or you can type it on the message. I'm sorry.
What's proof?
Dion bisa tulis, please type tulis di chat.
Yeah, can you type?
Okay, bro. Okay, bro. Wait.
So he is asking about magnetic energy or electromagnetic, how you deal with electromagnetic in your system or
Uh,
in your dynamic system. Is there any electromagnetic in dynamic system?
you mean the magnetic energy?
Yes, magnetic energy or yeah, other energy. And I think the question is about how to deal that parameters into the optimizations into the dynamic equation, for example.
Oh, I think for the magnetic energy, it is a very highly nonlinear dynamic system. So just like you mentioned that for the to deal with this highly nonlinear system, what we need to do, maybe we can use the AI to train the, the highly nonlinear system. But for a very simple or linear system, we just use the first order or the second order system to characterize the subsystems. Yes. So there is maybe here is a thing is that as I mentioned, here is a commercialized software, what we call it the ANSYS. The software of ANSYS is used for dealing with emulate the performance of different. For example, here is a subsystem to emulate the magnetic energy, but it's very time consuming. Well, the reason is why time consuming is that because you use the finite element so that you have to um, using the results and to do some average computation to get like a very low order dynamics maps, and then you can use the low order dynamics map, or you can use the very simple input output to feed to the neural neural network to construct the magnetic energy in your system. Because if you want to run the real-time simulation, your model should be very simple or with a low order. So if the phenomenon is very highly nonlinear, then you have to transfer it to a map or to a neural network, and then you can integrate it with different subsystems, and the model can be run in real time. Yes. Okay.
Okay, Prof. Thank you for your explanation.
Thank you for
Thank
your
you for
question.
your question. Uh,
Thank you.
because I'm interesting when I develop AI
Oh,
magnetics AI between system of reality, global reality.
mhm. Okay. Yes. But today my talk is focusing on a system level. So for system level, it's not related to the geometric relationship, the distribution, like distribution of the temperature, etc. So when we simulate it in the system level, your dynamic equation should be very linear or with low orders to abstract the key parameters from the subsystems. Yes.
Okay, thank you for the questions. Now already 20:07. It means that the time is over, but that's depend on the questions. If you are still interested in this lecture, of course, you may ask more questions, maybe one more, and then finish. Ada pertanyaan satu lagi? Is there any question? One last question. Okay, maybe no. Then, ladies and gentlemen, we have reached the end of our sessions. On behalf of the Magister of Data Science in the Faculty of Science and Mathematics, Satyawatana Christian University, we would like to express our deepest appreciations to Professor Yi Xuan Hung.
Yeah,
Sorry.
very precisely.
Yeah, okay. For his enlightening presentations and thoughtful discussions. We also thank for all participants. Would you like please to open the camera for uh, make picture together? So thank for all participants for your attention and excellent question. Of course, today's session has truly highlighted how artificial intelligence can empower green energy and electric vehicle innovations, paving the way for a smarter and more sustainable future. Of course. Once again, thank you very much, Professor Ung, and thank you everyone for joining us. Have a pleasant evening and see you in our next event. Professor Hung would like to give another uh, talk on 17 November.
I think this talk
13 or
is.
7?
I think it's just this talk. Yes.
Oh, just this talk. Okay.
Yeah. Thank you,
Thank you.
everybody. Thank you
Thank
for
you.
all of you, and thank you for your question. I think that's very great to inspire me for the future research. Yeah. Thank you very much for all of you. Yes.
Thank you very much. Please open the camera now. Take the picture together. Camera on. Somebody take the screenshot, please, because in my laptop only several, not all of the audience uh, use the camera. Maybe in your laptop more than mine. Okay, let's take picture together. 1, 2, 3, 4 again. One, two, three, four. Okay, thank you everyone. Thank you, Professor Hung.
Thank you,
Okay, thank
bro.
you. Thank you, Pak.
Yeah, thank you very much for joining us. Thank you.
Thank you very much.
Okay, thank you.
Thank you, bro.